Thank you, and thank you for having me. So I was excited to join you via teleconference today. What I wanted to do was share with you some work that my collaborators and I have been involved in machine learning and in deep learning. But before that, as you heard, involved in Coursera. I thought I'd say a couple words about that because Coursera really had its origins in a machine learning class that I taught. So, some of you might know my story, but as a Stanford professor, I used to teach a 400 student Stanford class. And about a year and a half ago, I put my class online and it reached an audience of 100,000 students. Since then, together with my friend Daphne Collar, we've taken the technology that my team had developed, which allows a single professor to teach 100,000 students, and we've developed a company, Coursera, that today partners with many of the top universities around the world. Here are the US universities. Here are the ones outside the US, including, of course, the Hebrew University of Jerusalem. And we're working with all of these great universities, including 30 of the 6 top universities worldwide, to create free online courses. So if at the conclusion of this talk, you decide you would like to learn more about machine learning or deep learning, there are actually free courses on Coursera today that you can take on any of these subjects. So on to the main topic of what I want to talk about. I'd like to share with you some ideas I'm excited about surrounding deep learning. This is a set of ideas that I think is making learning algorithms much better and much easier to use, and I hope will enable all of us to make revolutionary advances in machine learning and AI. I should say that most of the ideas I'm going to talk about are really not just my own, but shared with a large community of researchers, among them Jeff Hinton, Yoshi Benjo, Jan LeCun, Kochler, Yoram Zinger, and many others. So let's start with the basics. What do we want computers to do with our data? We wanted to examine images and label that as a motorcycle. We wanted to listen to audio and do speech recognition. We wanted to examine text data and do web search, anti-spam, and so on. About 2.5 years ago, I asked my students to apply a state-of-the-art technique, computer vision machine learning algorithm, to detect motorcycles. And this was the result that they got. Using state-of-the-art techniques, you end up finding motorcycles in lots of places where they don't exist. So even though machine learning is our best shot today at building all of these applications, I think that machine learning algorithms today are still very difficult to use. And each of these applications is easily 6 months or 2 years of work for a team of 50 engineers. And we also want our systems to perform better. So what is it about machine learning that makes it so hard to use? Well, those of us that teach machine learning classes like to present pictures like this, where we say, if you want to learn a motorcycle detector, take your data and feed it to the learning algorithm and let the learning algorithm figure it out. But of course, this picture isn't how machine learning actually works. Instead of feeding the data to the learning algorithm, what actually happens is we have to come up with a feature representation, and it is that feature representation that we feed to the learning algorithm. So this is true throughout different machine learning applications. In computer vision, we have vision features. In audio, we have audio features. And in text, we have text or natural language processing features. And there's always these features that we have to develop and feed to the learning algorithm. Given that the feature representation is the lens through which our learning algorithms view the world, this gives them a certain primacy, a certain importance. So where do you get these features from? Well, I think the state-of-the-art answer for where you get computer vision features is there have been teams of computer vision researchers that have been hand designing features. So SIFT is the single most highly cited paper in computer vision in the last 15 years, and it was invented by David Lowe, who literally took 10 years fiddling around with pseudocode to come up with a SIFT algorithm. The SIFT algorithm, I've read the SIFT paper maybe 5 times now, and even today I don't really understand exactly what it does. But it's a very effective feature in that it captures a few useful statistical properties and summarizes them for images. But is there a better way to come up with features than this? So this is computer vision. How about audio? Well, in audio, the state-of-the-art features are from the same process. Teams of thousands of audio researchers around the world hand engineering features for decades in some cases. And in natural language processing, it's the same thing. In fact, a good fraction of natural language processing research today is unapologetically about coming up with better features. In fact, why do we need parsers? Why do we spend so much time working on parsers? I don't actually want a piece of software to tell me where the noun phrases are in my sentence. I don't actually care. But the reason we spend so much time on parsers is in the hope that if a piece of software can tell me where my noun phrases are, that might be a useful feature for some downstream applications, such as web search, anti-spam, machine translation that we care about. So coming up with features is difficult, time-consuming, requires experts. And I'm speaking to you from Silicon Valley. And when I walk around Silicon Valley and look at applied machine learning here in the Valley, doing applied machine learning, basically sitting around hand designing features. And that's what is the most time-consuming part of designing learning algorithms. And in fact, if you look at this pipeline, the final box, the learning algorithm, whether you use a simple vector machine or a logistic regression or a softmax regression, that accounts for a relatively small fraction of the differences in performance. What usually accounts for a huge difference in your learning algorithm's performance is the feature representation that you design for it. So can we do better? And rather than having hand-engineered feature representations, can we have a learning algorithm to come up with the features automatically? So the next piece of what I want to talk about draws a bit from biological inspiration. Like many of you perhaps, I tend to treat biological inspiration with great caution and even a healthy dose of skepticism. But I think there's one piece of biological inspiration that has driven a lot of the work in deep learning. So let me share that idea with you. It turns out there is a fascinating hypothesis that most of human intelligence, a lot of human intelligence, may be due to a single learning algorithm, not due to hundreds or thousands of different algorithms, but due to just one algorithm. Let me share with you what some of the evidence for this hypothesis. Shown in this picture, that red piece of brain tissue is your auditory cortex, and you use that part of your brain to process sound. Neuroscientists have done the following neural rewiring experiment where you cut the wire to the auditory cortex and rewire the brain so that the signal from the optic nerve eventually makes its way to the auditory cortex. It turns out if you do this, your auditory cortex will learn to see. And this is the word see in every sense that I know how to use that word. When you do this experiment on animals, these animals can do visual discrimination tasks. They can look at pictures and make correct decisions, and they do so using that red piece of their brain tissue. In this slide, that red piece of brain tissue is your somatosensory cortex. You use it to process your sense of touch. If you do a similar neural rewiring experiment, your somatosensory cortex learns to see. So turns out there's a wealth of evidence like these two examples and many others, which suggest that to a surprisingly large extent, not always, but to a surprisingly large extent, it's as if you can plug in almost any sensor into almost any part of the brain, and the brain will learn an appropriate representation, an appropriate feature representation for that sensor's data. So if the same physical piece of brain tissue can process sight or sound or touch, then maybe the same algorithm can process sight or sound or touch. And if we can discover an approximation to that algorithm and implement it in a computer, then that might be a better way to come up with feature representations than having to separately hand engineer a separate feature representation for each problem. So motivated by this, here's a mathematical problem that I'd like to pose, which is that given a 14 by 14 image patch X, one way to represent this image patch is as a list of the 196 pixel intensity values. The problem I'd like to pose is, can we find a better feature vector? That is, can we find a more useful list of numbers than just listing out the pixel intensity values with which to represent that image patch? In order to develop an algorithm to do so, I'm going to turn to biological inspiration just one final time. If it turns out that if you look at how the human brain, how the biological brain processes images, the first thing your brain does when it gets an image is it looks for edges or it looks for lines in an image. So in your brain right now, there is probably a neuron that is looking for a 45-degree line or a 45-degree edge like that shown on the left. So an edge or a line is a dark region next to a lighter region. Right? And in your brain right now, there is probably a different neuron that is looking out, that is trying to detect a vertical line or vertical edge like that shown on the right. So this is how early visual processing, we believe, works in biological brains. So can we get a learning algorithm to do the same? There's a fascinating algorithm called Sparse Coding that gives a surprisingly good explanation of early visual processing, that is, of edge detection in the brain. And this algorithm does not depend on us hand coding edge detection or line detection. Instead, it discovers the concept of edge detection by itself. Here's how sparse coding works. The input to sparse coding is a set of M images, let's say M 14 by 14 image patches. And what it does is it learns a dictionary of basis functions. Let's call it phi 1 through phi k, where k here you should think of as maybe 64 if you're learning 64 basis functions. And it learns your dictionary of basis functions phi 1 through phi k so that each of your input training set images x can be approximately decomposed as a linear combination of your basis functions phi 1 through phi k, subject to the constraint that the coefficients aj's are mostly 0. Okay, so the constraints that the aj's are mostly 0 is called a sparsity constraint, and hence the name sparse coding. So I'll just leave the slide up for a few more seconds, and then you can look at it. All right, so this was the only equation that I have in this talk. So, I hope you enjoyed it. To explain the same thing in pictures, when you apply sparse coding to a set of natural images, sparse coding will learn a dictionary of basis functions like that shown on the right. Each of the little squares is one of, in this case, 64 basis functions learned by sparse coding. And when sparse coding receives a new test example like this, what it will do is it will select out a small subset, let's say 3 out of 64 basis functions, and it explains the test example as a linear combination of these 3 out of 64 basis functions. So notice a couple of things. First, sparse coding has chosen an edge detector for each of its basis functions. It could have chosen absolutely anything it wants for its basis functions, but 100 times out of 100 times that you run sparse coding, all of the basis functions will look a lot like those edge detectors shown on the upper right. Second, notice how sparse coding is decomposing this test example x shown at the bottom. It's saying that the image x is 0.8 times basis number 36, or times edge number 36, plus 0.3 times edge number 42, plus 0.5 times edge number 63. So what this does is it gives us a representation of this image in terms of the edges that appear in it. It's saying that this image is about 0.8 of edge 36 and 0.3 of edge 42 and 0.5 of edge 63. And this gives us this feature vector, this representation, A1 through A64 of this image. So this list of numbers, A1 through A64, it gives a more succinct, higher level, and more compact representation of the image X. That is, it's more useful to know where the edges are in my image rather than to know where the pixels are. And so this feature vector A1 through A64 gives a better representation, more useful feature representation. Here are a few more examples. Just to summarize, sparse coding gives a more succinct, this method invents edge detection and it automatically learns to represent an image in terms of the edges that appear in it. And neuroscientists have also done a quantitative comparison between the output of sparse coding and what's observed in the biological visual cortex, and shown that it gives a not perfect, but again a surprisingly good explanation for early visual processing in the brain. Here's a fascinating experiment that Evan Smith, did. And these are images that I got from Evan. What Evan did was he took sparse coding, so the same algorithm, and he applied it to auditory data. So what I'm showing here is 20 basis functions. So it's a grid of 5x4 images. So 20 basis functions that Evan obtained when he trained sparse coding on audio data. So what he did was he then went to a database of biological auditory processing data. We went to a database of what cat neurons in the cat biological auditory processing system are doing. And for each of the 20 basis functions learned by sparse coding, he found the closest match in biology. And the closest matches in biology are shown overlaid in red. And so the same algorithm, on the one hand, gives a surprisingly good explanation for early visual processing, and it also gives maybe a surprisingly good explanation for early auditory processing, just depending on what data you feed it, whether you feed it images or whether you feed it audio as its training data. So using one layer of sparse coding, what you can do is, in the case of images, you can show it some input pixels and automatically learn to group together pixels to form edge detectors. What you can do is recursively apply this algorithm so that rather than just finding edge detectors, you can also group together edge detectors to form higher and higher level features. This work builds on Jeff Hinton's work on learning DBNs. But to explain the same thing in pictures, what I explained earlier was when one layer of sparse coding allows you to group together pixels to find edge detectors, when you recursively apply this algorithm, then at the higher levels of this representation, you can, just as you can group together pixels to form edge detectors, you can group together edge detectors to form detectors of higher object features as well as of more complete object models. So just to explain what this means, right? This visualization and this first layer, that little square there means that at the first layer of this algorithm, we've learned one feature that is looking for, like a roughly vertical edge. This visualization here shows that one layer up, we have learned a feature that is looking out for an eye like that. And that feature fires, so that feature gives a large number when it detects an eye-like feature in the image. And this visualization at the next level up, that's a feature detector that is looking out for faces that look like that face. And of course, each of these feature detectors computes an increasingly and highly nonlinear feature of the input image. But for visualization, they're shown here as just what are the features that activates what is the image that activates that feature. I should say, in this particular result, each of these feature detectors were generated by training on a database that contained only pictures of faces. And so if you have a database and the database contains only pictures of faces and you train this sort of feature detector, then these are the results you get. So we've been able to apply sparse coding and apply recursive versions of these algorithms, hierarchical versions of these algorithms, to learn very complex features. What are these features good for? Well, one thing it's good for is for feature learning for machine learning applications. So going back to our very early example, let's say I want to train a system to detect pictures of motorcycles. With standard supervised learning, you'd have to generate a bunch of label data and train a learning algorithm on it. But with sparse coding, what you can do is now take a large collection of unlabeled data and apply these algorithms recursively to learn a very rich set of features just from unlabeled data. And then you now have a very good set of features that you can apply together with a small label training set in order to train a system to detect motorcycles. So applying this technique, it's called self-taught learning, we've been able to beat or substantially surpass many previously state-of-the-art techniques on many benchmarks. This is just one example in which we took a standard video activity recognition benchmark called the Hollywood 2 benchmark, and previously in computer vision, vision researchers had hand-designed features and, made some amount of progress from, I don't know, 38 to 47% improvement over some large number of years. A couple of years ago, Kwok Le, one of my PhD students, decided to just learn the features, and he was able to immediately substantially surpass the previous state-of-the-art hand-designed features. In fact, this sort of example is not at all uncommon today in machine learning and in deep learning and in feature learning. And both my research group at Stanford, as well as many other groups around the world, have been applying these techniques successfully in problems in audio, computer vision, video, natural language. And I guess in my entire professional career in machine learning, I've actually never before seen this many benchmarks fall this rapidly to so many different research groups before. And I think deep learning is very much taking the machine learning world by storm. And it's a state-of-the-art technique for so many applications today. So I guess the ideas I just described was maybe where we were, where the set of ideas were as of a couple of years ago. And what we did a couple of years ago was sit down and ask ourselves seriously, given what we know now about deep learning and feature learning, what is the next step? So given these ideas in learning features from unlabeled data, how do we go about building the highest possible accuracy learning system? One of the pieces of work that really inspired me was a piece of work that Banco and Bro had done over a decade ago, in which over a decade ago they were interested in the ongoing debates about what was the best learning algorithm of the day. Back in 2001, here were some of the leading learning algorithms of the day, and what they did was they took some of the leading learning algorithms of their day and applied all of them to a problem on which they were able to obtain a huge training set. And the four colors here, four lines here, represent the performance of the four different learning algorithms. And what you see is that the trends are very clear, right? It's as if exactly which learning algorithm you use doesn't matter. All four learning algorithms perform about the same. But what really matters is the size of the training set that you give these learning algorithms. So it's been results like these which has led to maxims in machine learning like that. In machine learning, it's often not who has the best algorithm that wins, it's who has the most data. And what we've seen over and over is that, a supposedly inferior algorithm will often outperform a supposedly superior algorithm if only the inferior algorithm can be trained at larger scale, or if you can give the supposedly inferior algorithm more data. So this is a result that Banco and Bro had generated over a decade ago using supervised learning, where the x-axis is the number of labeled training examples they were able to give the system. More recently, Adam Coates and I ran a similar study in unsupervised learning, where we use algorithms like Sparse Coding to learn features from unlabeled data. The interesting difference is that when you're training from unlabeled data, when you're in unsupervised feature learning land, then all of us have an infinite amount of unlabeled data. You can go onto the web and suck down as much unlabeled data as you want. So we're no longer constrained by the amount of data we have access to. All of us have access to an effectively infinite amount of data. But what matters is whether you have the computation to process the effectively unlimited amounts of unlabeled data that you have. So Adam Coates replicates a similar study where on the x-axis is the number of features, or really the amount of computational power you have to process as much as you can of this unlabeled data. And what we see is a similar trend where if you're learning features from unlabeled data, here these different colors are some of the different leading unsupervised feature learning algorithms of the day. And what we see again is a similar trend in which, exactly which algorithm you choose does matter, but what matters even more is the amount of computation or the size of the model that you're able to build, perhaps even more so than exactly what algorithm you're using. So because of that, about 2 years ago, actually slightly more than 2 years ago now, I went around Silicon Valley and tried to figure out, how can I find a lot of computers to build really, really large learning algorithms. And so fortunately, I had some friends at Google, and Google has had a lot of computers, and so I started a project. Founded and led a project in Google about 2 years ago to build up very large-scale deep learning algorithms using some of Google's massive compute infrastructure. And here I was fortunate to work with Jeff Dean, Quackler, many others, amazing team that Google had. So I want to share with you the results of the Google work. I'm going to break it down into two parts. It turns out that I think deep learning works well in two fairly distinct settings. And when people like me give talks, sometimes we confuse the two settings, but I'll try to keep the two settings distinct. The first is learning from labeled data, in which we take a massive labeled data set and try to have a very large-scale learning algorithm that can exploit that labeled data set. So what we did was we took huge neural network models like these, basically, sparse coding or recursive sparse coding, algorithms with a similar flavor. And we started by taking a model like that and partitioning our neural networks onto multiple machines so that we can distribute the computation across multiple machines, say distributed across the Google Cloud. Each machine, shown by the little light blue roundish oval round square there, can further exploit parallelism, in which we exploit multi-core parallelism within each of the machines. And because of the neural network being only sparsely connected, the amount of communication that needs to happen between different machines is relatively small. And so by taking huge neural networks and partitioning it across, say, on the order of 100 machines and maybe 16,000 CPU cores, we're able to start training much larger models than is possible on a single machine. So this is one layer of parallelism that we were able to build in. But in order to scale up to more than 100 machines, more than 16,000 CPU cores, we decided to build in another dimension of parallelism. So the diagram here shows one model instance, in other words, one single neural network that is distributed across, say, 100 machines. What we can do is take this model and start to make multiple copies of it. So what we can do is we can take one copy of the model and store all the parameters of the model in a distributed network of computers that we call the parameter server. What one instance of the model can do is do some local computation, do a stochastic gradient descent computation to decide what direction in which to modify the parameters. That model first sucks down the global copy of the parameters, does a gradient computation to compute how it wants to update the parameters, and it then sends the parameter update back up to the master copy of the parameters stored at the parameter server, and the parameter server can then apply this update to the parameters. And then the process repeats, where it can download the parameters again, compute this update to delta p prime, and the parameter server can just apply the updates that this model instance is computing. Once we have this architecture, we can then have multiple instances of the model, and each of the instances of the model can process a different subset of the data, so that you can have, say, 10 different model workers, so 10 copies of your global neural network. I've shown 3 here in this diagram, but you can have maybe 10, 20 copies, and each of the copies of the model can then proceed in parallel with its own gradient descent updates, and each of the model workers can asynchronously run as fast as it can and compute gradient descent updates to send up to the parameter server, which then applies the gradient descent updates asynchronously. So from an engineering standpoint, having these multiple copies of the model instances, of the slave models, is superior to having just a single model, because it gives substantially better robustness to if some of the individual machines are slow. When you're running on 1,000 machines, it means that at least one machine will die or just crash per day on average, right? So the mean time to failure of a machine is 3 years. That means that running on 1,000 machines means you have one machine die per day. And in fact, because of machines being preempted and randomness in network speeds and what's happening with a specific computer, there's a substantial variance in how fast individual models run. And by having multiple copies of the model, by having 10 copies, if one of the shards becomes slow or dies or drops out, you can just shut down that instance or ignore that instance, and the rest of the model, and the other, the rest of the model can then proceed without substantial slowdown. And so having these independent copies of the model has been really critical to running many copies, to running on 1,000 machines in parallel while remaining robust to specific model instances slowing down. So what is this good for? By ran some benchmarks in which we compared the large model to training using this formalism, using this distributed setup to train a small-scale model that fits on a single GPU, and no surprise, running on 1,000 machines results in much faster training than a single GPU. But the more interesting case is when you can now use the distributed models to train much larger models that cannot fit on a single GPU. And so this sort of very large-scale neural network training has been useful for multiple applications. One that's been announced by Google. This is really the work of Vincent and others on the Google Speech team. But if you use the Android cell phone, I think almost every Android cell phone today, certainly in the United States, I think probably in Israel as well, is trained on top of this sort of deep learning algorithm built on top of the large-scale Google parallel, the very large-scale neural network architecture that we have built, and Vincent and Hook on the speech team really did an amazing job training up this speech recognition system. The deep learning algorithms is used in a number of other Google applications as well, including processing some of the images on Google Street View, as well as a number of other applications that haven't been announced publicly yet. So what I talked about is the application of these ideas to learning from labeled data, in which we train the algorithm on a massive amount of labeled data. A second dimension, a second contribution is when we can take these algorithms and train them on a massive amount of unlabeled data. So, and this is really our attempt to take this result that I had shown earlier and extrapolate what if we can take the results much further to the right of this graph. So previously in deep learning, before I started the Google Deep Learning project, deep learning researchers were training models with maybe 10 million parameters, and the typical training set size was maybe 50,000 small images. With the distributed architecture we're able to build at Google, instead of training 10 million parameters, we're able to train models with 1 billion parameters and train on much larger data set sizes as well. So what we did, one fun experiment we did was we decided to take our 1 billion parameter model and we had it train on 10 million unlabeled images taken off YouTube. So imagine, if you will, that we have, like a little simulated baby brain. The simulated baby brain wakes up not knowing anything, and we're going to make it watch YouTube for a week. At the end of that, we're going to probe the neural network to see what feature detectors it had learned. So we had a hypothesis that it would learn to detect commonly occurring objects in YouTube. We know that faces occur frequently in YouTube, and we found that, lo and behold, one of the feature detectors it had learned was a face detector. So we had a feature detector that responds strongly to all of the images on the left, and the single most input that most strongly activates this image was a face detector. Was the face shown on the right. So I think this looks a lot like a face detector. So we found this because faces occur frequently in YouTube. Well, what else occurs frequently in YouTube? Cats. So perhaps reinforcing a stereotype, we looked and we actually found a different feature detector that looks, for all intents and purposes, like is a detector of cat faces. So I think learning these feature detectors was a useful technology demonstration, but these features have been useful for computer vision problems as well, in which we learned a rich set of features by training for a week on 10 million YouTube images. And then one of the problems we applied it to was ImageNet classification, where the task is to examine images and categorize them into one of 22,000 categories. This is a very hard computer vision benchmark where one of the tasks is to decide if an image is a manta ray or a stingray. Many of these categories are very difficult. So random guessing on this data set gives you 0.05% performance improvement. Shown here is the previous state of the art. And when we learn the features, rather than hand engineer them, our team was able to obtain substantially better performance than the previous state of the art. I think I would guess, some of us are guessing that human level performance on this data set is maybe around 30%. It's very hard to tell. That's a gut feeling intuition number rather than one backed up by data. But I think this is a substantial improvement in maybe the largest academic benchmark in machine learning. So since we built this work at Google, I've often been asked, what if I want to work on deep learning, but I don't have 16,000 CPU cores lying around? So starting, maybe around August last year, I stepped back from my Google role and at Stanford decided to work on using GPUs, putting GPUs, massive numbers of GPUs in order to scale up because most people do not have access to 16,000 CPU cores. And I guess this isn't work that I talked about much outside Google so far, but this is actually probably one of the hardest pieces of engineering that I've ever done in my life. But putting together 64 GPUs and doing some very, very tricky MPI and CUDA parallel engineering, we've been able today to build models with now over 10 billion parameters. So, roughly 5 to 10x the size of what we were doing at Google, and by doing very large-scale GPU implementations. So I think this is exciting that with relatively much lower-cost hardware, my Stanford team has been able to build maybe even larger neural networks than what the team I was working with at Google had back when I was working there. Yes. Oh, okay, fine. So yeah, I'll wrap up quickly, I guess. So just one more slide. Looking into the future, when I think about where machine learning should go, I think here's how I want to share with you how I think about machine learning. I think over the last decade, human ingenuity has been getting better with better and better algorithms, and as a result of that, human ingenuity has been causing the performance of learning algorithms to improve. But I think that there's a different effect which has been having a much larger impact on the performance of our learning algorithms, which is just the sheer volume of data that all of you in this room have access to. And as we extrapolate into the future, I think human ingenuity, shown by the red line, will continue to get better. But I think the learning algorithms of the future, the best performing algorithms in the future will be the ones that are able to exploit the rapidly exploding amounts of data that all of us have. And the reason I like deep learning is really just for one simple reason, which is that it happens to be a class of algorithms that is particularly good at exploiting either the label or the unlabeled massive amounts of labeled or unlabeled data that all of us have now, and that will continue to grow even more rapidly going into the future. And that's why I think deep learning algorithms isn't the only class of algorithms, but there's a class of algorithms that is able to continue to exploit ever-growing amounts of data, and that's why I think is a increasingly promising technology going into the future. Just to wrap up, talks about the idea of learning rather than hand engineering the features. And as an AI researcher, the problem that excites me most intellectually is whether or not we can really discover the fundamental computational principles that underlie perception. I know that a high-level talk like this has many pretty pictures, but it's hard to understand and implement these algorithms yourself just based on a high-level talk like this. If any of you are interested in mastering these techniques yourself, we put a lot of effort into developing a tutorial on deep learning. And so if you go there and work through the exercises and so on, then you will have implemented for yourself a state-of-the-art version of all of these algorithms and be, nearly at nearly a state-of-the-art knowledge in deep learning. And so to those of you interested in developing further these algorithms or applying them yourself as well, I hope that the tutorial listed there will be useful. And with that, let me just say, just acknowledge my collaborators again, most notably Adam Close-Kovler, Jeff Dean, many others at Stanford and at Google. And with that, let me say thank you very much.